have embedded the knowledge into the way we do our networks, and we take that for granted. Yeah.
Okay, yeah, cool. Oh yeah, that was a very good example. Like TCP kind of already takes care of the day-to-day Byzantine failures that we would be subjected to. Yeah, that's good. Cool. Do you want to talk about move to the next section, or do you still want to give some overview?
I think I would like also to talk a bit about safety and liveness.
Let's talk about safety and liveness.
Safety and liveness come from automata. So think of a sort of a program.
When you say
as a
automata, what do you mean? Can you define that term for?
Yes. So think of a program as a transition system. You have states, and you transition between these states based on the actions that you perform on the state of your machine. Safety means that something, intuitively here, it says that nothing bad ever happens. So which means that you never will, in this transition system, you will never find yourself in an error state, or in a state where your data is inconsistent, or a state in which, let's say you have an exception, or you have an error, you have a division by 0 somewhere. You never find yourself in one of these bad states. Of course, doing nothing, just doing absolutely nothing with your program, will keep you safe, but that's not something that you want. So then you have to talk about liveness. You have to talk about something will always happen, something good will always happen, which means you, in every state you are, for instance, you can transition to a different state. If you are in an error state, usually you don't have transitions outside of that error state. So once you have divided by 0, you don't want to transition in another state from that one. So you kind of have to terminate the program. And you have to be in a good state as well. And unreliable, the fact that we talk about unreliability is that we talk about different transition systems that have communication channels between them, and we have faults, right? As Bogdan mentioned earlier, messages may not travel correctly from one place to another, may never reach the other party.
Nice. So, yeah, go on.
And the transition between the states of the system in general, which is a combination of the states of each of your transition systems.
Yeah.
You are in a safe place, and you also have your system has liveness, so you can keep sending messages, you can keep communicating, you can go to a different state.
That's interesting. Yeah. So with liveness, the way I see it is basically you always get a response to your request, right? But I wanted to ask if it's, for example, if you would get an error response from a service, would that count as liveness, availability, or not?
It depends on how your system is organized. So if you are able to deal with error messages, then your system is alive. If you are not able to deal even with good messages, if you receive a message that you don't know how to interpret, then you're not in a good state.
Okay, well, that clears it. Thank you. Because I was thinking of, for example, if you work with S3, when does the service officially become unavailable, right?
I cannot tell you that, I'm sorry.
No, like live, okay.
I cannot tell you that.
Good. Okay, do you want to move on?
Yes, finally. Finally done with the introduction.
Yeah, okay. So again, you have consistency. I'm going to repeat it just for myself to make sure I understand it. Consistency basically says it's a property of security, and basically says that nothing bad would ever happen, right? And then availability, yeah, is that good?
I wouldn't make the connection just yet.
Okay.
I wouldn't make the connection between consistency being one or the other just yet. I think we'll go through the paper and find out.
Okay, fine. But until now, this is how I understood it. Consistency is a property of safety, and then availability is a property of aliveness, and then we're gonna have a look at the interplay between the two, right?
Yeah.
Cool. So the interplay between the two. I think in this section, it starts out by talking about how the initial CAP theorem was defined and in what context. And from what I got it was defined in the context of a web service with geographically distributed services. Clients send a request to this web service, and then they get a response. That was kind of the whole context of the service. Later on, it goes on into defining this web service more in depth, saying that where is it? It can be a simple service, and then gives a bit more details of the operations. But then, as an initial context, this is what I got from the CAP theorem.
Yes. Yeah. So partition, again, just partition tolerance means that some of these processes may be disconnected, unable to communicate, rather than your data actually being partitioned on in different processes.
So apparently the original context, we have someone in chat saying that the original context, according to Lynch's 2002 paper, is a distributed data store. Data store can read and write a value. And distributed equals multiple node on multiple servers, which is good. And I think the paper goes into saying this later on, right? That they're talking about a web service which provides read-write operations on a shared data store, and all of the operations get a response, and they're also atomic, right?
Yes, so this paper does go back to that one in multiple places, and a distributed data store is one example in which we can have these properties.
Cool. Thank you. High five to the person that said this. I like it. I just want more interaction, because I think this is when it's fun, like when you interact, like multiple people interact and share ideas. So let's go back to the paper. So again, let's focus. CAP theorem is being discussed. We're discussing it in the context of this data store, distributed data store, which you can have read-write which you can do read-write operations, and then all of the operations get a response, and then the operations are atomic.
Yes. I think so. We do have here a bit of an explanation of an explanation of what consistency is and different flavors of consistency. For instance, if you don't deal with data that is changing, for instance, such as here, you always return the same values, or if your data is naturally partitioned, let's say you have a lot of geographical data, say maps, information about businesses nearby, and so on, and they are static. For instance, businesses are not going to move. A shop is not going to move every time interval. Then you don't necessarily deal with the CAP theorem. So you don't have to think about consistency in this scenario of maintaining consistency, because you don't have changes. You can simply partition the data per, let's say, county or country or whatever, and you access the process or the server that deals with that data. So you don't have to think about consistency. And that's not one of the examples that we're going to use here. We also have weakly consistent data, which is it gives the example of a distributed web cache. It's data that it's okay to change less often. And here, one of the things that I see in this weakly consistent model is that it doesn't explain why they are okay to be weakly consistent. But nowadays, for instance, you have a lot of reads from some of the services, but you don't have lots of writes. For instance, news, or think of Reddit. You have a lot of read. I was going to say Reddit. You have a lot of read. Everybody reads, but you don't have as much posting or as much comments or whatever. And even if you want to look at upvotes, it's fine if you see 6,000 instead of 6,152 people upvoting a certain post, right? So it's fine if you maintain a cache and you provide that one.
Yeah, that is definitely the way to go for a content consuming world and for websites as well. And I guess there are a lot of ways of providing a weak consistent service, and especially with caches and everything. So I feel like it would be nice if this paper would have went in to discuss them more in depth, but we're going to focus on that trade-off between consistency and availability right now.
Yeah. Also, there are services. So consistency, it's not explained here, but in real-world services, you may have consistency, for instance, per operation or per sequence of operations. So you can have read after write, or if you have consistency, you have eventual consistency that is also guarantees the order of operations. So if you're going to, if the guaranteeing of order of operation is that if you read the value, you're never going to read a value that was before that, right? And so on. But this is a whole other discussion.
Yeah, I was going to say, I think you're going into some eventual consistency, and sounds to me a bit like a service that we all know and love, which was eventual consistent up until recently. We're talking about S3. So yeah. So are you saying that those services, so for example, let's say eventual consistent service that does consistency based on operation, would that be classified as a weakly consistent service?
Yes, it's definitely not strong consistency.
Okay.
So it's a weak it's a weak consistency.
What if it gives you strong consistency 98% of the time, but 2% it gives you weak consistency? Is that still weak consistency?
Well, it depends on how you want to look at it. For instance, if you want to think, you can, so systems nowadays, databases, storage systems, sometimes they offer consistency per operation. They say, we have these operations, these are consistent, and these are our weakly consistent operations, or eventually consistent. Not many of them enter into the nitty-gritty or the very fine-grained consistency specifications. But when they propose something to the customers, they say that they guarantee consistency or not. So usually you have, but they don't say, so for instance, you said that you will have consistency for a window of time, and then for another window of time, you will not have consistency. That I haven't seen that. The paper does say that these systems exist, but I don't know from my own experience.
Yeah, I was gonna say because they talk about this tool that can do the trade-offs, but I think it's quite impractical. I don't know, and I've never heard of it. So maybe we can talk more about it when we get to that section.
Oh, actually,
What?
um, I'm not sure. So I am speculating here, but I do know that content delivery networks have periods of times when some content is more popular than another content. And metadata for a specific type of content will be changed more often, for instance, likes, reviews. So that one may potentially fall into this category. When the content is popular and there is a lot of interaction with it, then you will probably want to increase certain guarantees about that. But when the content is not popular, then it's fine to sit in the lowest drawer of your delivery network
Actually,
and not care so much about updating it.
yeah, that's a good idea. Yeah, it's a good point. I was seeing something more like they were talking about airline reservations with seats becoming popular and things like that. But so I thought there's this dynamic tool that changes stuff, but it makes sense to have this cache that basically keeps all of the most common things in memory, like the most accessed metadata, and then that's how you can basically balance out this trade-off between consistency and availability. Good point. Good point. Okay, moving on. Availability. Yeah, go on. Moving on just a bit to availability. Go on.
Availability, in this case, refers generally to deadlocks, starvation. So a system is unavailable. A system can become unavailable once you don't receive a response. But in more practical terms, it could be deadlocks. If there is a communication between your servers, one of them may be deadlocked on a resource or maybe starved on that resource. If you, for instance, if you have a bad algorithm for choosing how do you share the resource. Yeah, so that's also one of the things that enters into the availability umbrella.
Got it. And I think it's also worth mentioning, but the paper mentions that a slow response can be consistent, like depending on the system requirements, a slow response is as good as or as bad as no response at all. So that might affect your availability as well. Because it goes on to later on talk about asynchronous systems and then how this trade-off can be proved to be impossible in an asynchronous system, which I think is important to have in mind.
Of course, you're not going to wait forever for somebody to eventually answer.
Yeah, and I think maybe as a thing to keep in the back of your mind, which I haven't thought about it that much, but when you interact, let's say you build an application that interacts with a service, a very important thing to have is to set your timeouts, because if you're working with a service, so for example, if you have a web app that works with some data store, it's very important to set the timeout, because that data store's timeouts basically become part of your system right now. If you let them run for 3 minutes, 4 minutes, it will take you 3 minutes, 4 minutes. But if you cut those timeouts, then you can improve your performance. So it makes you think about what the system actually is and what it involves. Like it can involve your mobile application, right?
I'm thinking of another physicist joke. If requests in their highest percent, like the lowest requests are like gases, they will fill all the time that you give them. All the timeout, the entire timeout that you give them, they'll fill all that timeout.
Yeah. So we have another comment, which is pretty good. It's like a cheeky way to beat the CAP theorem availability. sorry, a cheeky way to beat the CAP theorem. Available equals a response must arrive within a million year. Yeah. Well,
Right.
yeah, that's a good one. By that time, we'll have fusion reactors, so maybe the computer won't burn out or something like that.
Yeah, it will give you a response and you will not even remember the request.
It's isn't it the same thing as the Hitchhiker's Guide to the Galaxy? It's like 42. Wait,
Yeah.
what was? Well, a million years ago, this response was interesting. Okay, so partition tolerance. Do you want to discuss partition tolerance, or do you feel like we've already talked about it enough?
I think it would be bad for me to give a third warning what partition means.
What does partition mean again?
Well, I think it says here, yeah, I think it talks about reliability. If it's unreliable, then it's prone to be partitioned. So you may have parts of your systems that are disconnected and unable to communicate.
Yeah, and then one thing that like you said, like pick two, you have consistency, availability, and then partition tolerance. And pick two, initially the way I thought about partitioning is it's like partitioning describes the underlying system, right? It's not like consistency describes your system, and then availability is like your system, but then partitioning describes the underlying communication right between them. It's not necessarily a property of your system. Partitioning, if that makes sense, is more like a property of the underlying communication system.
Yes.
Yeah, but then another, like a better way that I think you can put it, and I got this from you, it's like you have consistency, availability, and then distributed system, right? And then you can pick two, because you can either have consistency and a distributed system, or availability and a distributed system, or consistency and availability, but then you don't have that distributed system because you probably have your network in an office and then that's it, right? Where you protect it very well.
Yeah, I don't really agree with this view.
Okay, go on.
Yeah, I don't really agree with this view because first of all, because no, you're not necessarily going to have either of them. So you can't if you use the internet, or if you use a communication system between your partitions, it's not going to be completely separated, because you don't have to pick 2 out of 3. You can get a third one, or you can get partly. You can get weak consistency and availability, and partitioning hopefully not going to happen that much. So there is a balance between them, and there are so many options on how you can. There are not just 3 options. Pick 2. If you pick 2, then you have only 3 ways of building your system. But there are actually more than 3 ways of building your system. You have different levels of partitioning. You have different levels of consistency and different levels of availability. And you have other problems that you may need to solve that will certainly impact your C, A, and P.
Yeah, okay. So I'll take what I said, and then I'll add what you said, that there's different levels of choosing between C and A, and then it's more like it's not just 1 and 0 binary. It's like different steps along the triangle. If you see a triangle, it's like different steps along the triangle where you can choose consistency and availability. And then,
I agree more with this one, yes.
yeah. And then chat says C and A, you can choose them. P is something that happens to you. Yep. And then P isn't even a choice anymore. Preach.
Yeah, you'll definitely need a distributed system.
Yeah. Well, you never know. Who knows how networks will evolve in the future? Who knows? Anyway, should we talk about the proof?
Yes. first thing that I noticed in this proof is that if I ever started a proof with, this is kind of straightforward to prove it correct, I think I would have been dismissed of my classes.
Just get out of my class. What do you mean it's straightforward? What does it, I can even see people like, what does straightforward mean? How do you mean? Like, what did you prove?
Or I actually remember writing this in my thesis, and then I had to go back on it, and I read that, and it didn't seem straightforward at all, at all. It was when I wrote it, but it wasn't when I read it.
If you take into consideration the fact that I haven't slept 12 hours and I've wrote this in my pajamas at 4 a.m. in the morning, it's quite straightforward.
Yeah.
Yeah, and then again, the user, like the chat user is quite right. Like the proof is fairly formal. Lamport papers have much more formal proof, sequences, functions. None of this is here. And yeah, we talked about Lamport last week and 2 weeks ago. And even for, I don't know, just passing time around, not just passing time around, you know, the proof for logical clocks was very thorough, adding physical clocks and how far they can drift apart. I couldn't understand it, but it was perfect.
Yeah, indeed. So it does follow quite easily. If you paid attention so far to the paper, then it does follow quite easily. So just to state it again, in a network subject to communication failures, it is impossible for any web service to implement an atomic read-write shared memory that guarantees a response to every request. And to make it clear here, shared memory means that you have the same data in multiple processes, or if you have a distributed system, well, you have access to you have the same data. Not so much. So it can be extrapolated, not so much the shared memory between like the exact same memory address for two processes on the same machine, but the same data in accessed by every process.
Yep. And then the atomic part of read-write, I think it's worth mentioning that they talk about atomicity as a property of safety. So basically, from a user's perspective, the request only happens once in the service. That's what makes it atomic, right?
Good point, yeah.
Yes, I did it. I made a good point. I can just leave the stream right now. Yeah, so the proof, just to, I don't know, yeah, just to overstate it. If you have one server that's here and then one server that's here and you don't have any communication between them, there is no way for this server to know what this server actually did with the requests, if it accepted them or not, and there is no way to communicate this in between them.
Indeed.
Yes. And as a quick side note, it also states that if the system was, if the communication was completely asynchronous, so basically asynchronous, no upper bound, messages can take 1,000,000 years. If you had one failure in the system, then again, you can guarantee consistency and availability for your system, because you don't know if it takes 1,000,000 years because the server failed, or just because it takes 1,000,000 years to do the computation, which is quite nice. And I think, was it Lynch or no? I don't think it was Lynch, because there was this paper in the 80s that basically proved that eventual consistency, eventual synchronous systems which are eventually synchronous are basically practical, because the synchronous ones are impractical just because you don't really know what happens to them because you don't have an upper bound, and then synchronous ones are impractical because it's very hard for them to basically guarantee that synchrony, right? So synchronizing the clocks and knowing exactly how long a request will take. So there was this paper that basically said that in a distributed system, the best way, I don't know how to put it, the most practical way is for a system to be eventually synchronous. That's all I remember. It was a good paper. Maybe we should do it at one point. So let's dive deep back into the future, back into the past. And then this section talks about the theoretical context between safety, liveness, and unreliable communication. And this is the section where we talk about replicated state machines, Paxos, and all the good stuff, right?
Yes, I think we definitely discussed early on about safety and liveness. And I think we can go to agreement.
And this is agreement in the context of consensus, right?
Yes.
And then consensus means that, consensus means two processes have to agree to one value, two distinct processes have to agree to one value. And for this to happen, you have to have agreement, which is every process must output the same value. Validity, the value that's being outputted has to have been an input value at some point. And then termination, which is every process must eventually at one point output its value. And as the paper says, you can clearly see that agreement and validity are of consistency, and then termination is availability. Agreement and validity are secure properties, and then termination is liveness.
Right.
Thank you. No need to clap.
Yes, I think this part starts talking about the fact that the old having the old liveness versus safety is related to the fact that it's a generalization of the CAP theorem, and it has been a problem in theory. So in formal settings, it has been a problem, a subject of discussion before CAP theorem.
Yeah, and basically this discussion gave birth to distributed algorithms that solve the trade-off between liveness and safety, and then one of that in the context of consensus, and then one of that distributed algorithms is Paxos.
Yes.
And I think they do they talk about it and this coping with liveness and safety trade-off for consensus, or did they just like briefly say that it happened and that's it? Can't remember.
So they start talking about how you can do the trade-offs. So for instance, you have consistency or partitioning. Partitioning, even if you have a distributed system, we don't usually think about partitioning as we can't communicate with another party. We usually think we can't communicate for a short period of time, or
messages are lost.
Or some messages are lost, yes. And they do talk about ways around it. So if we have, so they ask how much drift between, how much partitioning is there, can we cope with? Can we cope if one is temporarily out in outage, 2, 3, all servers are in outage?
And did they do this in the context of synchrony? Because I think this is what I remember, right?
Yes.
Yeah, and then it goes on to say the fact that you can only achieve consensus if you have smaller, if there is a number of failure which is smaller than n/2, where n is basically the number of servers in your system, right? Because I know they build up from synchrony, which I don't know, I kind of skipped because I already knew that you can only achieve consensus when you have more than half servers, more than half of your servers aren't failed, right? Are still up and running, basically. And they do talk about failure detectors, which introduces the concept of primary and, well, what was the... It's a leader and follower. I didn't want to use the M and S words, but you have the leader and follower.
Yes, yes. So the leader election, you have a leader, and then that one tells, I mean, can do something like, are you online? Are you online? And this goes around in all servers in your system.
Yeah, heartbeats. And
Heartbeat.
then, yeah, and I think it's quite a nice algorithm as well, like the leader election, because it sends heartbeats, and then when the followers, if they don't receive the heartbeats, they go like, ooh, maybe I should propose myself as a leader, and then that whole leader election process starts, and I think it's quite fun.
Yeah. So the paper doesn't really talk, I think,
It doesn't
about
talk about this.
it does.
No,
Oh, yeah,
no,
it doesn't. It doesn't talk about leader election, but it does talk about the oracle. So that leader you can choose either way you want, and you can have that algorithm as you want. But what Bogdan was saying, this is the most common way to do that.
Yeah, thank you. And I think that's we can go into consistency or jump into practical implications. What would you prefer? Do you know anything about this case set agreement paper?
Sorry, which one?
So in this consistency topic, in this consistency section, the paper talks about, you can see it on the screen, the paper talks about this case set agreement problem, where you can basically show that the most agreement you can get in a system with k-1 failures if you want to ensure availability. Go on.
Intuitively, I don't remember if I read this paper. Probably I didn't, but I do kind of understand this area. I believe I understand it. So if you have one partition, you will have one result. So your agreement, you will be able to agree on the same value, right? You have one partition, everybody communicates correctly, you are able to get one result, to get the same result everywhere, or to output the same value.
Okay, so 2 partition, 2 results, 3 partition, 3 different results?
Yes.
Okay.
Now, how do you get from one partition to 2 partitions? You have to remove a minimum one connection, especially if you have the bottleneck one single connection. If you remove that one, you have 2 partition, and that is the minimum you have to remove to get from one partition to 2 partitions.
I hope you're right, because it sounds interesting.
So this is my intuition.
Okay.
This is how this is underlying the explanation in the paper, that to get 2 different results, well, it goes directly from getting 2 different results to getting one bad connection.
That is interesting. Thank you.
So that's the minimum. Of course, if depends on your network topology. So if you have at least 2 ways of getting information from one place to another, then removing one, it's not gonna influence.
Yeah.
But it's at least one if your network topology is such as having a single edge at some point, a bottleneck. Yeah.
Makes sense. Nice. Should we jump into the practical implications?
Let's do that.
And honestly, this is what I like about the paper. It's like, despite the negative implications of the CAP theorem, practitioners building distributed systems still must do the impossible. It's like, Yeah, we proved that it's impossible, like theory-wise, but let the engineers do the impossible and come up with trade-offs, and let them deal with the actual building of the systems. This is how I read the paper. So I have a different translator voice in my head. So, first trade-off, best effort availability. And this section gives an example of Chubby, and the way that I see it is basically if you have a network that's reliable enough, you don't really have to worry that much about availability. So that's like the best effort availability. So you focus a lot on consistency. Is that true? Did I get that right?
Can you repeat that?
Okay, so this section talks about best effort availability, right? And then it talks about Chubby, the Chubby service.
It does talk about Chubby service, and it does talk about best effort availability.
And
So that is correct.
yes, and the way I got like the way that I got this the best effort availability, the way I understood it is if you have a network that's reliable enough, you don't have to worry that much about availability, so you focus a lot on consistency.
Yes. This is what I got. This is what I remember.
Good, because I was just double checking. Sometimes I read papers and I get something completely wrong. So it's nice to achieve consensus, right? Because the network is not partitioned. Not yet, anyway. If BT holds up. Oh, jinxed it. Anyway, what did you find interesting in this best effort availability section? Before I start ranting.
I think it talks about, so at the beginning it says that it guarantees consistency, that is correct operation regardless of the network behavior, but also it can be seen as correct response. So I think it's interesting that, so it does talk about strong consistency on Chubby because it has a primary backup design. So if the primary fails, then the backup will take its place. But yeah, it is still going to work as the primary. And then it starts discussing the fact that you can do, if you have read-only operations, or if you have a balance between operations, then you can ensure more than two of them. So more than, you can ensure different levels of consistency. Here, for instance, it says that read-only requests are prioritized.
So basically read-heavy workload, right?
Yes.
Do you know, have you read the Chubby paper? Have you read the Chubby paper?
I don't remember.
Yeah.
I don't think so.
Yeah.
Let's say no.
Yeah. All I know about it is it's basically described in this introduction of Chubby. It's a distributed service, and then it provides this way of working with the service, like the operations that it provides the same operations that you would have on a file system. And the reason why it does this is you can literally store some metadata very quickly, and then you can create these structures to synchronize in between services. So, for example, as you said with the leader partition service, so if you have a service that wants to achieve consensus, the master will basically write a file at one location, and then everyone from the master got it. Damn it, I used the master word. But anyway, you know the slaves are looking at that file location in the distributed system, and if the lock is there, you're basically the master is still alive. And then if the lock is not there, it's time for an election, and then whoever writes the lock there will become the master. So that's how I got it. That's what I got with Chubby is. It's basically a super. It is a service that works mostly, like, it's optimized for metadata and small small workloads in that sense. Like it doesn't do a lot of data throughput, and it's optimized for fast operations. So you can achieve these,
Yes.
Yeah. So that's all I know about Chubby. And I don't think I even explained it nicely, so I'll have to read the paper just so I can explain it better.
I think it another good point here is that even if it doesn't guarantee availability, so it says here, Chubby provides guaranteed consistency and a very high level of availability in the common case. So if they chose consistency over availability, but that doesn't stop the system to be pretty available most of the time, usable.
Yeah, and then one of the reasons why it's chosen like this is because they have this is in context of Google, right? So they have this in a data center, right? A Chubby cell, like a Chubby, I don't know, deployment is basically called a cell, and then that lives in the data center. So I don't think there's that much communication between the different Chubby cells. So anything that happens from like Google file system point of view or Bigtable or whatever they're using it for is happening in one cell, one data center. So availability drops in a data centers are quite rarely encountered, right? So I think this is why they went for this design. And just like any distributed system, it's basically saying that at one point the primary will fail. This is normal, like you're going to have a failure, and then if that fails, please take that into consideration when you're writing requests for it, and then retry or just give it some time. I think it states this at some point, so I like it. It's talking a bit about how to handle that extra edge case of when the availability drops down, which is best effort basically, right?
Yes.
Nice. Best effort consistency, unless you wanted to say something else.
Yes. I think this one touches on the example that we talked earlier, such as content distribution, where you need access as quickly as possible. So when, for instance, you open Reddit, or Twitter, you expect to see something. Even if
it's out of date, yeah.
Yeah, even if it's 1 hour late, 2 hours late, doesn't matter, but you expect to see something.
Yeah. And I think it's quite amazing the fact that they look at availability, like the way they do best effort availability again is by but the way they do they would guarantee this availability is by moving and pushing the web content to web servers which are geographically located to users. So this is how they would do, like they would offer this high availability, which I think is quite interesting.
Yes, of course. And as the content is farther geographically away, it also tends to take longer to update, to be updated.
Yep, that's true. And I think, was it Netflix that kind of did something similar? Like this reminds me of Netflix because they went to ISPs, to internet service providers, and then they put their own boxes in the ISPs just so they can basically have their own CDN, right?
Yes.
So, nice one, Netflix. Good job. They read the paper. Okay. And then trading consistency for availability. And this is that great scenario that you gave an example of, where sometimes you will have hot content and that needs to be more available and less consistent, or more consistent and more available at some point than the other type of content, right?
Yeah.
It
also
go on.
It also talks about the network connectivity hasn't been good recently. We don't talk about this, at least not at the hour or day granularity, but instead we do talk about processes, other resources that impact on communication. For instance, you have multiple things running on the same machine. be it in the cloud, it's a virtual machine, for instance. There are so many things going around it. And that can impact how quickly messages can pass or how quickly the state of your system changes. And even though the network is not necessarily a problem, other things can be. Queuing, contention is a problem.
Noisy
The processes
neighbors.
run. Sorry?
Noisy neighbors.
Yes, noisy neighbors. That means processes on the same
Yeah.
server.
Yeah, not literally. My
On the
noisy
same
neighbors.
Yeah. So I think this one still stands.
That is very true. That is true. Well, I was quick to judge, but it's good that I cleared this out. It's important. So now the paper goes into segmenting consistency and availability. It's basically, from how I got it, it's how you could, it's like some guidelines on how you could do the trade-offs between consistency and availability when you're building these distributed systems. And one way of doing it is on data partitioning, right? The example that it gives is like an e-commerce platform. Users don't really mind if the product description is a bit out of date or something like that in the whole website, but they do mind if their billing is wrong or checkout. Anything that's related to money has to be strongly consistent.
Yes, if you are able to partition data such that it doesn't, you don't need to access much data from a different partition, then you're good.
You're good.
Yeah, if you don't have to do any join in your database, you're good.
It's actually, there's this, I didn't read the paper. I just read a bit about the introduction and something around it. There's this concept of doing a database, Noria. I don't know if you heard about it. And the way it tries to do joins and everything is basically, as you do joins and whatever you do with your database, it will internally push data closer to your join. So for example, you have a join statement and a select statement, and then another statement, right? So as you do these joins and operations in your database, data gets cached at different points in your operation, right? So whenever you run the same statement again, the data is already there cached, right? So it's another way of doing caching, which I found it quite interesting. I have to understand it a bit more, but I quite like this idea. And it feels like it takes, in a way, care of data partitioning, in a way.
Yeah, that sounds interesting.
We will do that at some point. Okay, operation partitioning, go.
I think, what does it say here?
It's the put get
example
that you gave.
Yes. This one is the example that it is the example that I gave, that some systems offer per operation consistency. For instance, you will see that some storage system may have read consistency, write consistency, or read after write.
Okay.
I'm not talking about, I'm not talking about the storage system that I work on, as I never do, but you may find on the pages, on this public information, that they do that, and extensive papers that explain that. And I think functional partitioning is somehow in a similar category, because you have different, for instance, a storage system or a database, you have different functions or functionalities. So some of them will offer you consistency, some of them may not.
Yeah, and then the point that this paper makes is that sometimes from the theoretical overview of your service, it might seem like you're trading both consistency and availability, right, at the same time. And then you're getting, depending on your functionality or operation, you would get one which is stronger at some point and then the other which is stronger at another point. Yep. User partitioning.
Oh, this is one that I actually dealt with a lot. I actually dealt with a lot.
Oh,
When I was doing my PhD thesis, I was working on these virtual worlds, games basically, or mixed reality worlds, also games where you have avatars or entities of your users moving around. And most systems actually do have a real where that can accept a maximum of, say, X hundred of people or of avatars. Or you can have geographical partitioning. Let's say you have this town. And then if you, in your virtual world, move to the next town, it's going to be a different partitioning. Basically, you are changing servers. You're communicating with a different server. Or you can have dynamic partitions which overlap. And you have users from you can see users from two different servers around you. And that can mean either that you communicate with both of these, or that these servers communicate to exchange information and have that shared memory, which is their overlap. And my contribution was having this overlap as seamless as possible and extending or contracting as it needs, as the distribution of the world changes.
so in the risk of going too deep, can you tell me in one sentence or two sentences how did you do it?
Well, I used a mathematical structure underneath, but I'm not going to talk about that. I use a triangulation underneath.
Thanks.
But you have, let's say you have people on a map, and they tend to be concentrated in different points. You will have a town center, let's say, that has lots of people. So there you will need to have more partitioning. But as time changes, as time goes on, these people will move and they may form groups, or they may concentrate in a different part of the town, which is, the festival, let's say. Then your partitioning will have, your data partitioning will have to change there. It will have to be more granular there. And you need communication between the servers that deal with the data to recalculate the partitioning.
That's quite interesting. That's good. The example that I had in my mind was basically Facebook. Like I thought that they would partition based on your friends. I think it also mentions that. And
LinkedIn does that. Like you cannot. I'm not sure
LinkedIn.
That you can.
Sorry, go on.
You cannot search more than 3 levels or something like that.
I don't know.
Anyways.
Yeah, I was gonna say that LinkedIn does that visually. Like you actually know the people which are your first connection, your second connection, your third connection, and because they have such a huge graph. There's always, I don't know, 4 connections between you and Bill Gates, something like that. So
yeah,
I think that's funny.
And because we're on the trade-offs, I'm going to tell you what the trade-off was for my solution.
Okay. What was it?
You had servers on each partition that were communicating with partitions nearby, and you were able to have a partitioning between servers. You wouldn't have communication between servers that didn't have close partitions, that weren't dealing with close partitions. So you wouldn't necessarily, you would have a lower response from your world if you were teleporting on the other side of the world, where you wouldn't have already a connection with a server nearby. So if you were just walking, you did offer the system that window of synchronization to be able to communicate with the next one. But if you were immediately changing, it would have been harder. It would have taken longer time. And the system would break if everyone, of course, would do this all the time, would just teleport here and there all the time.
Yeah, and I mean, the way that games take care of this is by putting loading screens everywhere. So this is why.
Yeah.
Yeah. I didn't know that. Thanks. Going back, I think this also, like your example, ties in a bit into hierarchical partitioning as well, because if you think of an application, you would have some communication at a global scale between the different servers, and then as you go down, you would have some servers based on regions, and then countries, and then in the country between cities. So that's how I saw hierarchical partitioning. And I don't know, I kind of like these papers that give you hints, like tools on how to build distributed systems and how to think about data before you just like start diving into and then designing something that's completely obscure, but it's well programmed. So I like this paper.
Yeah.
Moving on to future. What do we have?
We have the fact that C, A, and P are not the only ones. There is an S, there is a T, and there's a W.
Yeah, W, and then turn upside down, it's mobile networks. What? Okay, scalability. Yeah, I think this is one of the trade-offs that every system has to keep in mind when it's being designed. The way I'm thinking about it is it that relevant if depending on the size of your service and the size of your company, it may be relevant or not. Because if you're a startup and you're trying and if you're trying to like build a product, you're gonna go to a cloud provider, and then scalability isn't that big of a deal if you just use like the basic tools and that. Or am I oversimplifying it?
No, I think it's important to understand a lot of the times, especially nowadays, a lot of the times you're not going to build a system from scratch. You are going to use something that already exists. You'll probably have to choose between different databases, and you'll have to understand why you choose the one that you choose. Which one is the best for your needs? Is it the one that offers eventual consistency? Is it the one that offers read after write consistency and so on? And if you're going to think about a big system eventually, are you going to, what is your bottleneck? You have to understand that even a distributed system that provides a good amount of these characteristics, is it going to scale or is it not going to scale? This is important as well. For instance, you have your leader election. That leader has limited resources, so it cannot deal with a lot of other services, servers around it. Yeah.
So playing into your example there, it's one of the last lines in this paragraph. It's basically, if we're going to study more about scalability, then we might even understand why it's so difficult to scale consensus protocols. Because if you think about it, the more servers you have involved in consensus, the difficult it would be to achieve that consensus, right? Because if you have, I don't know, 50 servers, and then by the time they all agree on a value, it would just take you a lot of time because it's the latency between them, the protocol. So yeah, scalability seems to be not necessarily a problem for the builders. I mean, there is the problem for the builders, but I think scalability in terms of consistent protocol and consensus protocols is going to be a challenge or an area of research as well.
Yes.
Well, I just read the paper. It's not my idea. So thanks for agreeing. Next thing is tolerating attacks, which is quite important nowadays. I think security, thankfully, is getting a lot more attention than it used to. And yeah, this paper, which was what, 9 years ago, basically says denial of service attacks are something to be taken into consideration every time you build a service, and I cannot agree more with it. But it's so
Yeah.
difficult. Like, I don't know.
Especially if your system is geographically distributed,
Yes.
so the farther apart your components are, the easier it is to cut the network connection, or the easier it is for something to happen, either delay or problems with your DNS.
Yep, that is true. Yeah, and then exactly, this is what it says, like major disruptions from internet services. And I think this is why a lot of data centers, they just choose to have their own specialized networks between the different data centers, right? Like, you're not necessarily gonna, I mean, you're gonna rely on an internet service provider, but they're gonna install definitely like your own landline or something like that. You don't wanna be sharing the network connection. And then the last one, the W, the wireless networks, talks about maybe how, not maybe, how distributed systems have evolved and are evolving right now. Like, we use a lot of our traffic comes from mobile networks, right?
Indeed, yeah.
That is true. And then I think one of the problems with mobile networks that this paper highlights is the fact that geographical proximity becomes more of an issue. Mobile networks are unreliable. Like, you can't really, sometimes you'll have good connection, sometimes you'll just have like very long latency, and then sometimes your network might drop. Like, you have to design a system that is capable of either having some local cache, storing, buffering all of these requests in memory, and then send them out at some point. So yeah, I think it's quite interesting. Is there some literature around these trade-offs?
There is definitely a lot of research on mobiles and network systems, mobile and wireless systems, sorry, within the area of network systems. There is definitely an increase in latency in wireless networks. There's more inconsistency in latency as well, because sometimes there are places where people are more concentrated, network is used more, places where it's not. Changing cells is also different. It adds up for these variations. Security.
Yeah, the changing in cells. I'm happy that maybe, I don't know, like, I'm being optimistic, but I think if when we switch from TCP to UDP, we won't have, when you're on WhatsApp and you're talking, and then you move from one wireless network to your mobile phone, you have that interruption, and then that's basically TCP just trying to bind the connections again. Apparently UDP would do it much faster or easier without interruption, just because it's a broadcast protocol. I don't know.
And of course that comes with its own problems, unreliability, but yeah.
Exactly. And then user says, our favorite user of the day says that CAP Theorem applies not just to the backend database, but also to mobile system. If data is on the mobile client and connection goes down, what do you do? Consistency, prevent an operation, availability, modify data offline on the app, and you lose consistency. That is very good. It's a very good point. I like it. High five. Cool. We're done. We are done with the paper for the day. Whoa. Longer than 1 hour than last time, but it was definitely worth it. I loved it. Chat, by the way, feel free to ask questions anytime. Write anything you want. Interact with us. And I got a heart. Thanks. I'm just gonna give a heart as well. You should join Twitch chat, Rolka. I'm gonna give a heart from you as well. From Rolka. Cool. that concludes our broadcast for today. We will see you in 2 weeks. Is that true? We're gonna keep this bi-weekly schedule. That is true. Do I have a thumbs up from you, Raluca? See you in 2 weeks.
Yeah, hopefully.
Yeah, hopefully, if if your life is consistent and your route to work is available.
If I'm live and safe.
If you're live and safe, yes. What's the next paper? It's a good question. So I have a list of papers, and I think I will publish it on Twitter or somewhere. Like, I feel like there's not a good place where I can interact with people, but I'm gonna start putting it on Twitter or in some form, and then we can vote on it, because the intention with the stream was to start kind of in the distributed space area with papers and then tackle the classical paper. So that's why we went for Lampard clocks. That's where we're talking CAP theorem. We have some chain replication that's also pretty good coming up. A view stem replication control, like some pretty good papers. But the short answer is I don't know. The better answer would be I will post the list on Twitter, and then we can all decide on it. And then yeah, like the people will decide. This is democracy.
Give power to the people.
Yeah, give power to the people. So I don't know, I can just promise a good selection of papers, and then after that, after we're done with distributed system, anything that people are interested in or we are interested, we can dive into CPUs. Oh, I think at one point it would be so cool to cover Turing's paper.
Oh, yeah.
Yeah, because I read it a long time ago, and it just blew my mind. Like, how can he be so have such a good foresight about what's gonna happen?
Academic archaeology.
Yeah, academic archaeology. Back in my day.
Back in Turing's day, it was like this.
There were bulbs instead of transistors. Yeah, so keep an eye on Twitter or the website. I will put up a list of papers. We will vote on it, and then in 2 weeks' time, we will discuss it and have fun.
Cool.
See you in 2
See you
weeks'
then.
time. Bye. Wait, how do I close the stream? Oh, I'm such a noob.